Countably infinite sets can be put in a one-to-one mapping with the real numbers, 1, 2, 3. Cantor proved with a diagonalization argument that the set of real numbers on an interval from 0 to 1 is uncountably infinite. This seems wrong to me, so I created a one-to-one mapping for this real number interval to the natural numbers. The mapping can be expressed in two equations, one for the forward operation and one for the inverse operation. The forward operation assigns a real to each natural, and you can see that equation in the middle of the table on the upper left. The equation on the right, it's the one that's like n minus p2 minus 1 plus m all over p1. And the one for the inverse operation of finding the natural associated with the real is shown in the equation on the left, starting with r times p3. The equation on the right is for the forward operation, real to natural, or sorry, natural to real. And the equation on the left is for the inverse operation, real to natural. This is a one-to-one mapping. There's, every real is going to have a natural number. Every natural number is going to have a real, and you can just pick a real number, any number of digits, and you can plug it in and calculate it. It's going to give you a natural number. We can't evaluate irrational numbers in these equations, but these equations show us how to do the mapping. P1, M, and M2 use the floor function. Digits, you'll see that on the left side there, is a function that provides the number of digits past the decimal has between 0 and 1. So for instance, 0.91, it's highlighted, has two digits. It's highlighted on the right-hand side. It has two digits, not an infinite number, because trailing zeros are excluded in this digits function. The equations are also shown in Python format on the left side of the screen. This code right here was used to generate a table of outputs, so we can see how this would map all the real numbers. As an aside, these Python functions do not run into rounding issues up to n equals 3000. Afterwards, the more complicated versions of the functions are required to catch rounding errors. Remember, we can't actually evaluate a real irrational number because they extend forever. The more robust version of the code was tested up to n equals 1,000,000, along with other large random integers and rationals, and the expected ordering and inversion behavior continue in these instances. So I was able to plug in, an n, get a real number out, and then use that real number, plug it into the inverse function, and get the exact same n that I started with. And I tested that for a bunch of different real numbers, and my only limitation was machine epsilon. So back to the mapping scheme in the large table of outputs. This mapping starts with the largest real numbers, 0.1, 0.2, and then goes to 0.9. And after all items of a particular order of magnitude are mapped, the algorithm proceeds to the next lower order of magnitude, 0.01, 0.02, 0.03, and it goes all the way up to 0.99. Notice that 0.99 is indexed with index number 99. And so in this 0.01 to 0.99, they're skipping items that have already been included in the list. In this table, the algorithm, and in this table and in the algorithm, we're skipping all the previously used real numbers in the interval of 0 to 1. So the first example in the table is index 18 and 19. Notice how n equals 18 corresponds to a real number of 0.09, but n equals 19 passes over 0.10, which is already covered by n equals 1, and moves to 0.11. This skipping behavior is captured by the variable m. And the above functions encode the behavior of creating finer meshes of the space as n increases. The index values n correspond closely with an analog of normal counting, as is shown in the smallest table on the right. Also notice skipping over previously included numbers creates index values that fit in the same broad bins as the real. It corresponds closely but not exactly with normal counting. So to see how it's close but not exact, you look at n equals 90 and 91. M, which is the thing that's doing the skipping, m increases between the two indexes of n equals 90 and 91 such that m minus parentheses p2 minus 1, close parentheses, that is evaluated to -1, where n equals 90, that little piece of the function is evaluated to 0 when n equals 91. So -1 at 90, 0 at 91, and r is 89 for 90, and that's a difference between what the real number is by, it's a difference of 1, and that's where the m is creating that difference. Whereas when n equals 91, r equals 0.91, which has a difference of 0. Whenever entering a new order of magnitude, 9 to 10, 99 to 100, etc., m resets back to 0. And when n reaches the last 9 elements of an order of magnitude, there's going to be no offset. As n approaches infinity, the number of digits in r also approaches infinity, and the set would eventually include both 0 and 1. The inverted function takes a real number input and provides the index that corresponds to r. So it's one-to-one both ways. Both forward and inverted functions cannot evaluate an irrational number input because n would be in the infinite, because there's an infinite number of digits. Whether or not the functions can be evaluated in these extremes, the mapping scheme represented still seems to map the set of all real numbers in the interval between 0 and 1. And so this interval is countably infinite, at least that's what I think right now, but I could be wrong. And so I don't think it's uncountably infinite like we all seem to think, or that's the common thought. And that is if there's no errors or problems with this. And we also may need to throw away our category of irrational numbers because, maybe just an irrational number is only irrational because our vision is limited to one side of infinity.